This will be the third lecture over chapter 15. So in this chapter we'll look at the molecular orbitals of alkenes and dienes and use that to lead into an introduction to what's known as UV Vis spectroscopy. So if we take an alkene, so if you recall, both of these carbons are sp2 hybridized, and if they're sp2 hybridized with a double bond, right, one of them is pi and one of them is a sigma bond. And what is the pi bond formed from? It's formed from p orbitals, right? P orbitals that overlap side to side to make a pi bond. So electrons have wave-like properties. So if you have a wave, right, then you have a positive and a negative phase. So sometimes when you see p orbitals sketched, you see them sketched like that with a plus or a minus, or you see one side shaded and one side not shaded, and this is just the shading is just representing the different phase, since the electrons have phase-like wave-like properties to them. Okay, so when two p orbitals, so p orbitals or atomic orbitals, so when I say atomic orbitals, that means s orbitals, p orbitals, d orbitals, f orbitals, if you remember from quantum mechanics back in General Chemistry 1. But when two p orbitals overlap with each other, when you let them overlap, then they make what are known as molecular orbitals. In this case, they make a molecular orbital known as a pi orbital. But when pi is formed, you also form what's called pi star. And the difference being, so pi is a bonding orbital and pi star is an anti. It's an anti-bonding orbital. So let's back up a little bit just to review, to remind yourself of what's going on here. So carbon has 4 valence electrons, right? And so it's got 3 sp2 hybridized orbitals. So if you remember, so carbon's electron configuration is 1s2, 2s2, 2p2. And if we represent it like this, so energy, low energy to high energy. So the 1s2 electrons we ignore, right? Those are the core electrons that are not participating in bonding, and it's only the 4 valence electrons that really matter. So what we're going to do first, if you remember, is we're going to take an electron out of here and put it there. So now we have 4 unpaired electrons, right? 4 valence electrons on carbon. But now what we're going to do is we're going to take 3 of those orbitals and we're going to mix them together. So we're going to take the 2s, and for drawing purposes, I picked the 2px and the 2pz. So we're going to take the 2s, the 2px, and the 2pz, and we're going to mix them or hybridize them to make 3 sp2 orbitals, right, that look like this. So they have a big lobe and a small lobe. And that's what's going to be used to make your sigma bonds. So if we take those 3 and position them, right, so we make 3 sp2s, each has 1 electron in them. And if we position them around carbon to maximize the distance between them, we would put them trigonoplanar, right? So that would be the sticks, right? sp2 this way, big lobe here and a small lobe there. sp2 there, small lobe on the backside of carbon, and this sp2 going on the big lobe, a wave, and then a small lobe here. But we don't really care about the sp2 orbitals, it's the p orbitals that matter. So each carbon also has a p orbital that's unhybridized. And each of them has 1 electron. So 2 carbons, each has a p orbital, and then we're going to let those come close enough together in space that they can overlap. Right, but when they do that, they could either be in phase, right, or they could be out of phase. So we'll try to represent that so here. So they could either be in phase when they come together. So basically what we're doing, if you remember what an orbital is, it's a mathematical description of the probability of where an electron can be found at. So when we're letting orbitals overlap, what we're really doing is math. We're really taking the equation for this orbital and the equation for that orbital, taking the equation for both orbitals and we're adding those equations together. We're doing math. So we could either add those equations or subtract those equations. Right, we could either add them or subtract them. And subtracting them is equivalent to adding them out of phase. So subtracting the equations for these two orbitals would be the equivalent of adding the two out of phase. Okay, so if they're both in phase and you let them overlap, then now you get an orbital that looks like this. Or simply or simply that. Or if they're out of phase, then your new orbital looks like this. So here there would be constructive interference between the two orbitals. And if you think of them as waves, if two waves are in phase when they meet, they have constructive interference. But if two waves are out of phase when they meet, they have destructive interference. So then this would form what's called pi, and then you also form pi star, because you have to consider both mathematical possibilities. So you make pi and you make pi star. This is bonding, because both are in phase, and this is anti-bonding, because both are out of phase. And how many electrons? Well, each carbon had one p orbital, and each p orbital had one electron in it, so we have 2 electrons. So just like atomic orbitals can only have 2 electrons, molecular orbitals can only have 2 electrons each as well. And so bonding is more stable than anti-bonding, so those 2 electrons will be in bonding. And then if you remember what the arrow up and arrow down means, they have opposite spin, right? If you remember, ms is plus 1/2, or ms is negative 1/2. Okay, so that's for a simple alkene. You can either have the p orbitals in phase, bonding, or you can have the p orbitals out of phase, anti-bonding, but there's 2 electrons, and the 2 electrons are in the bonding orbital. And so both of these orbitals exist on the alkene simultaneously. It's just that there's 2 electrons in this one, and there's no electrons in that one. So no electrons in that one. So we could do the same analysis for a diene. So if we have a diene, then we have 1, 2, 3, 4 p orbitals. So if we want to take into consideration the combinations of in phase and out of phase, so we could have all 4 of those p orbitals in phase. So we're going to go from low energy to high energy. Or we could have, so here we have 0 nodes. So a node would be a phase change. So there's no phase changes in there. They're all 4 in phase. Or we could have 1 node. Right, where 2 are in phase and 2 are in phase, but in the middle they're not in phase. Or we can have 2 nodes. Right, or they could all be out of phase. In which case there's 3 nodes, right? There's 3 phase changes. Okay, so that's what the pi system would look like for a diene with 4 p orbitals. And then how many electrons? Each p orbital can have 1 electron, so there's 4 total. And so where are those 4 going to be? Well, they're going to populate from the lowest energy to the highest energy. So pi 1, pi 2 is higher in energy, so 2 there, and pi 3 has none, and pi 4 has none. So then pi 2 and pi 1 and pi 2 would be bonding orbitals, and pi 3 and 4 would be anti-bonding orbitals. Okay, so some other terminology that you see in this type of analysis. This is what's called the highest occupied molecular orbital, and that's what's called the lowest unoccupied molecular orbital. So the LUMO, so lowest unoccupied. So unoccupied just means it does not have electrons in it. So that is the lowest energy orbital that does not have electrons in it. And then pi 2, that is the highest energy orbital that has that is occupied, or occupied means it has electrons in it. Okay, so the significance of this is that you can study these molecules by using what's known as UV or visible spectroscopy. So a UV Vis instrument. So this is basically how a UV Vis instrument works. So you have a UV source, so it generates a UV beam, and then you can split that beam using a beam splitter and then reflect it off of mirrors. And so now we have a beam, two UV beams from the same source. And so we'll pass one of those through the sample. So this would be your molecule, typically dissolved in some solvent. And then you would have a reference, which would typically be the same type of holder. The holder's, whatever's holding your sample, made out of the same material. But the reference would just contain solvent and no sample in it. And then those two UV beams go to hit a detector. So for UV radiation, so we're talking about 10 to the minus 9 nanometer wavelength, so about 200 to 400 nanometer. And in the visible region of the spectrum, that would be about 400 to 800 nanometer light. So about 2 times 10 to the 5th minus 5, or 4 times 10 to the minus 5 centimeter wavelength. If you remember what wavelength is, right? It's just the distance between any two similar points on a wave. Okay, so what happens when a molecule with a pi system, so pi electrons, absorbs UV or visible light? If it's the right frequency, then it'll undergo what's known as an electronic transition. So basically that means the electrons can absorb the radiation and they can promote to a higher energy orbital. So for electrons in pi systems and for electrons, for lone pair electrons, that energy just happens to fall in the UV and visible region of the spectrum. So for a simple alkene, for example, ethene, then it's got pi 1 and pi 2, right? So this would be the highest occupied molecular orbital, and this would be the lowest unoccupied molecular orbital. And so 2 electrons in a pi system. What happens if you shine light on it? Or so H nu would be the symbol for light, right? So that basically just means electromagnetic radiation. That could be gamma ray, X-ray, UV ray, visible, microwave, infrared, radio wave. If it's the right frequency or the right wavelength, then an electron can absorb that energy and promote to a higher energy orbital. In this case, it would go to pi star. So this would be what's called your ground state. And then this would be what's called the excited state, where electron is in a higher energy orbital, in this case pi star. So you've populated now the anti-bonding orbital. Okay, so for ethylene, the energy needed to do this is light of 171 nanometer, so about in the UV region. And so that would be light that possesses 688 kilojoules of energy per mole. So if you had a mole of ethene, you would need 688 kilojoules of energy to promote 1 electron from every single one of those molecules from pi to pi star. So then this is what your UV typically looks like. You just plot on the vertical scale how much light is being absorbed, and on the horizontal scale you just plot wavelength. So ethylene would absorb at 100. So you would see a peak at 171 nanometers. So what does that mean? So that just means whenever the wavelength hit 171, now that electron started absorbing that energy and it moved up to a higher energy orbital. And then of course eventually it's going to come back down and it's going to give off energy. Okay, so the key equation in UV Vis is that equation. So A is absorption is equal to epsilon times B times C. So epsilon is a constant. It's called the molar absorptivity. So that is just the fundamental constant for the molecule. And every molecule has its own epsilon value. B is the path length. So that would be that would be your cell. So if you have a UV beam and you shoot it through your sample, so B is just however wide that sample is. So as you can imagine, the wider it is, then the more your UV beam, the more molecules your UV beam will interact with, so more light's going to be absorbed. And C is concentration. So again, the more molecules that are in solution, the more molecules will be available to absorb some of that UV radiation. So basically, absorption is directly proportional to concentration. As concentration goes up, then your peak would get bigger. So you can use, if you know the constant epsilon and you know your path length, then you can measure your absorption and you can figure out what the concentration of your sample is if your molecule absorbs UV visible light. Okay, so if this was butadiene, so we looked at, this is what the molecular orbitals for the pi system for butadiene look like. So if you shine light on it of the right frequency or right wavelength, then you'll promote an electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And now your electron configuration would look like that. So for butadiene, you need 217 nanometer light to cause this electronic transition. So 217 for butadiene and 171 for ethylene. So which one's higher energy? So if you remember, as wavelength goes up, energy goes down. So you need less energy to promote an electron for butadiene than you do for ethylene. And so this is the trend that will look like. So these two double bonds are conjugated, right? So every time you put another double bond in conjugation, the energy gap between highest occupied and lowest unoccupied gets smaller, so it requires less energy to promote an electron. Right? So again, so every time a double bond is added in conjugation the keyword, right? The energy gap between pi and pi star becomes smaller, so you need less energy to promote an electron. So if you put 3 double bonds in conjugation, right, you only need 258 nanometer light. 4 double bonds, you only need 290, so less energy. 5 double bonds, 534. Whoa, that's not right. 5 double bonds, 334. Right, 6 double bonds, 362 nanometer light. So again, wavelength is getting longer. So the energy required to promote that electron is getting smaller. And so 7 double bonds, so now this is significance. So that only requires 400 nanometer light. So the significance of that is you are now in the visible region of the spectrum. Right, all of these are in the UV visible region. Right, these are all UV. About 400 nanometers in the visible region of the spectrum. So the significance of that is that this molecule will have color. So in general, color comes from molecules with lots of double bonds in conjugation. Once you have 7 double bonds in conjugation, the molecule will have color. Or it could come from atoms in the molecule that have, if you have a metal in the molecule that has D and F electrons, then you can promote electrons from D and F orbitals, and that can absorb in the visible region of the spectrum as well. Okay, so that's an example. If we take this molecule, it's one you're all familiar with. This molecule is called beta. Beta carotene. So you find that in oranges, right? What color, or not oranges, and carrots. Right, what color are carrots? They are orange. Why are they orange? Because this molecule absorbs 454 nanometer light. So it absorbs blue light, and of course what you see is what's reflected. So the light hits the beta carotene absorbs the blue component of that visible light, and what gets reflected to your eye is visible light without blue in it, and that appears orange to you. Right, so if you took the UV of beta carotene, it would look like this. So you just start scanning through at 454, it absorbs light, it absorbs UV light. So what's going on is an electron is being promoted in the pi system to a pi star orbital. And so if you remember the acronym Roy G. Biv, right, so this is about 454, so it absorbs blue light and then it appears to you as orange in color. Okay, so that's a couple of more examples of this. If we take this molecule, this is a molecule you're probably all familiar with from general chemistry, maybe high school chemistry. So if you take this molecule and react it with base, so base takes a hydrogen off here, these electrons can go there, these can go there, these can go there, and then this ring can open up. So the significance of being, so this molecule is colorless if it's neutral or acidic pH, because the benzenes, you only have 3 double bonds in conjugation with each other. So that would be in the visible region of, or UV region of the spectrum where it absorbs. So UV, not visible, so you can't see it. But once this reaction occurs, then now you have all of these benzene rings are in conjugation with each other, right? You have 1, 2, 3, 4, 5, 6, 7, 8, 9 double bonds. Nine double bonds in conjugation. This molecule has color. It's pink. This molecule is phenolphthalein. It's an acid-base indicator. So an acid, when it's acidic, then this hydrogen is on that oxygen, and none of the double bonds are, and this ring is closed, so none of the double bonds are in conjugation. So it doesn't absorb in the visible region of the spectrum. But when it's in base, then this reaction occurs, and that opens up that ring. That ester, that lactone ring is opened up. Now all of these double bonds are in conjugation, and now the molecule has color. It absorbs in the visible region of the spectrum. You find this useful in protein chemistry as well. So these are 4 amino acids. This is phenylalanine. It's got a benzene ring. 3 double bonds in conjugation. This absorbs in the UV region of the spectrum. It absorbs at 257 nanometer. This is tyrosine. It absorbs at 257 as well. This is histidine. If you notice, it's only got 2 double bonds in a lone pair, so it absorbs at a lower wavelength, so higher energy. But that's still in the UV region of the spectrum. And this is tryptophan, which if you notice, it's got 1, 2, 3, 4 double bonds and a lone pair in conjugation. So it's going to absorb at a higher wavelength, lower energy. But the point is all of these absorb in the UV region of the spectrum. And so this is useful because now you can detect if you have a protein that contains these amino acids, you can detect that protein using UV spectroscopy. So that could be useful in a biochemistry, biology setting if you're trying to analyze for proteins. Can be used in forensic chemistry if you're trying to analyze for a protein, medicinal chemistry if you're trying to analyze for a protein that may be expressed. Okay, and it's one more example. So if we take this molecule again, so beta carotene. So in the liver cleaves this bond in liver enzymes to make this, and oxidizes those carbons to alcohols. So you make what's known as vitamin A. Also called retinol. What does the OL mean? If you remember, that's how you name alcohols. And then retinol, this alcohol can be converted to an aldehyde. So would that be an oxidation or a reduction? Right. That would be an oxidation. So retinol gets oxidized to retinal. That's how you name an aldehyde, is with the AL ending. And so here all of the double bonds are trans, and this double bond gets converted enzymatically into the cis isomer, to the cis, and you make what's called 11 cis retinal. And then that gets attached to a protein called opsin. So a free amine of opsin reacts with this aldehyde to make this carbon-nitrogen double bond. If you remember what that functional group is called, it's called an imine. And the significance of this molecule is, so this molecule then is basically the fundamental basis of vision. So when this molecule, when light hits this molecule, it causes this double bond to isomerize from cis to trans. And that process takes about 200 femtoseconds, so about 2 times 10 to the minus 13 seconds. And when that isomerization occurs from cis to trans, that generates a nerve signal, which is sent to the brain. That's interpreted as vision. And then now you have the trans protein, which then gets isomerized back to the cis, and then this process can occur again. So without the protein present, this process would take about 1,100 years. But in the presence of the protein, this isomerization with light can occur in femtoseconds. And why does it occur? Because if we take just a simple double bond, for example, so normally with a double bond, you can't rotate around the double bond, right? Because it requires too much energy to break that pi bond, because to rotate you would have to break the pi bond. But once you promote an electron from pi to pi star, then there's only one electron in the pi system. There's only one electron in the bonding p orbital, so that bond is weaker, and now that rotation can occur more easily. Okay, so anyway, but that's the fundamental basis of UV Vis spectroscopies. You can promote an electron from pi to pi star, and then that has consequences. One consequence would be is that now you can rotate around double bonds more easily. And another consequence being that now you can do UV Vis spectroscopy and you can monitor that. Okay, we'll stop there.